All right, if you're an aspiring embedded engineer, you know there's one topic that can totally make or break your technical interview: communication protocols. So today we're going to demystify the big three: UART, I2C, and SPI, so you can walk into your next interview with complete confidence.
So, how do you ace it? Landing that first embedded job can feel like this massive mountain to climb, but honestly, the path forward is a lot clearer than you might think.
It really all boils down to one thing: understanding how components actually talk to each other. I mean, think about it. Microcontrollers, sensors, memory chips, they're all in this constant conversation. And these protocols, they're the languages they speak. If you can master them, you've pretty much mastered a core concept of all embedded systems.
Okay, before we dive into each protocol one by one, we've got to nail the single most important concept that divides them. It's the difference between synchronous and asynchronous communication. Get this, and you are already halfway to acing that interview, I promise. And this right here, this is the classic interview question, so listen up. Synchronous communication, that's what I2C and SBI use, is kind of like a band with a really good drummer. There's a shared clock signal, this steady beat, that keeps every device perfectly in time. That's what allows for super fast, super reliable data transfer. Now, asynchronous, which is what Uart uses, is like that same band trying to play without a drummer. Yeah, they agreed on the tempo beforehand, we call that the baud rate, but without that constant beat keeping them locked in, their speed is just fundamentally limited.
So, let's kick things off with the simplest of the three. Everyone, meet Uart, the reliable, no-frills workhorse of the embedded world.
The name really says it all. Universal, asynchronous, receiver, transmitter. At its core, it's just a way for one device to talk directly to one other device. The two key things to remember here are asynchronous, which means no clock, and point-to-point, meaning it's strictly a one-on-one conversation.
So you might be asking, how in the world does it work without a clock? Well, it's all about a predefined structure, a handshake agreement. The line is usually sitting idle at a high voltage. Then a start bit suddenly pulls the line low. That's the signal to the receiver like, hey, wake up, data's coming. Then you get the actual data bits, usually a byte, so 8 bits, followed by a stop bit that brings the line back high. All that's required is that both devices agree on the timing, the baud rate, ahead of time.
And here's a great feature. Because it has two totally separate wires for transmitting, that's TX, and receiving, RX, UART is what we call full duplex. Think of it just like a telephone call. Both people can talk and listen at the exact same time without interrupting each other. This is absolutely perfect for things like a debug console where you're constantly sending commands and getting info back.
Okay, so UART is great for those one-to-one chats. But what happens when your microcontroller needs to talk to a whole room full of devices at once? Well, that is precisely the problem that I2C was designed to solve. I2C, or Inter-Integrated Circuit, is just brilliant. First off, it's synchronous, so it has that clock signal we talked about. But here's the magic trick. It can connect a huge number of devices. We're talking up to 127 of them using just 2 wires. How does it do it? Every single device on that line gets its own unique address.
And the way it works is actually pretty cool. Think of it like a conference call. The master device first gets everyone's attention with a start signal. Then it calls out a specific name. That's the 7-bit address. Only the device with that address is supposed to respond, and it does so with a little acknowledge signal, or ACK bit, which basically says, yep, I'm here, ready to talk. Then they exchange their data, and finally the master hangs up with a stop signal. It's that simple.
Now, I2C is amazing for connecting a ton of devices, but it's not exactly a speed demon. So what if your number one priority isn't the number of devices, but pure raw speed? For that, you're going to need SPI.
SPI, or Serial Peripheral Interface, is all about one thing: performance. It's synchronous, it's full duplex, and it was built for one primary purpose: to achieve the highest possible data throughput. We're talking about things like streaming pixel data to a display or reading from high-speed flash memory.
But that speed comes with a trade-off, and this slide shows it perfectly. SPI uses dedicated lines for everything. There's one for data going out from the master, MASI, and another for data coming in, MISO. And instead of addresses, it uses a chip select line. To talk to a slave, the master just pulls its dedicated chip select line low. It's super simple and incredibly fast, but as you can see, the number of wires you need just keeps growing with every new device you add. It can get messy.
Okay, we've got the foundations down. You know how each one of these works, so now let's put it all together and figure out how to answer the questions you are actually going to face in that interview.
All right, if you're going to screenshot one slide from this whole thing, make it this one. This is your ultimate cheat sheet. It summarizes everything: the clock type, whether it's full or half duplex, how it addresses things, its speed, and its ideal use case. I'm telling you, this table is the key to unlocking almost any comparison question an interviewer is going to throw at you.
Okay, let's do a little rapid fire round. First question up, an absolute classic. What is the main advantage of I2C over SPI?
The answer, in 2 words, is wiring and scalability. With I2C, you can hook up a whole mess of sensors and chips using the exact same 2 pins on your microcontroller. If you tried that with SPI, you would run out of pins on your chip almost immediately. It's all about that hardware efficiency.
All right, next question. And you can bet they will almost certainly ask the reverse. So what's the main advantage of SPI over I2C?
And the answer here is all about speed and throughput. SPI is just way, way faster. We're talking 50 plus megabits per second compared to I2C's standard 400 kilobits per second. Plus, its protocol has way less overhead, and remember, it's full duplex. So when you need to just blast a fire hose of data, like for a high-res display, SPI is, without a doubt, the champion.
Now for a practical scenario. Imagine this. You've got a project. You need to connect 10 different sensors and 1 EEPROM chip for memory. What's your pick?
Yeah, the choice here is crystal clear. It's I2C. Trying to use SPI for those 11 devices would need at least 14 wires. It would be an absolute wiring nightmare and a total waste of your precious microcontroller pins. I2C handles it so elegantly with just those 2 wires. And since sensors and EEPROMs aren't usually high-speed devices anyway, it's the perfect tool for the job. And you know, that really brings us to the most important takeaway of all. There is no single best protocol. It doesn't exist. A truly great embedded engineer doesn't just know what UART, I2C, and SPI are, they understand the trade-offs. They know how to look at a problem and choose the right tool for that specific job. So I'm going to leave you with a final challenge to chew on. Imagine a weather station. It has 5 different sensors: temperature, humidity, pressure, you name it. And it also needs to log all this data to an SD card. Which protocols would you use for each part of this system? And more importantly, why? Really think about the trade-offs we've discussed. That's the kind of critical thinking that will help you absolutely crush that interview. Good luck!